In 4.2, we're talking about differentiation and the derivative. Really what we're talking about here are rates of change, just like I had said before. Well, if we want to look at the way something is changing in two variables, usually what we've learned in the past is called the average rate of change. And this compares the change in my y values to the change in my x values. In other words, if maybe I have 2 points like I have here, x1 and x2, and well, their function values would be f of x1 and f of x2. I'll just write them the other way for now, because it'll look more familiar if I do. The change in my y values, the change in my x values. Well, this looks a whole lot like slope. Right? This is just the slope formula. And that's exactly what I'm talking about. When I talk about rates of change, we've seen this before. Rates of change is modeled in math using the slope. We're going to talk about a different couple types of slope in this video, essentially. And we're going to start with the slope of what we call a secant line. So a secant line is a line that intersects a curve, just generally intersects a curve. And usually we're going to talk about two specific points. I'm going to call them x1 and x2. If I want to find the slope of that secant line, x1 and x2, again, I want the change in my y values. So we'll stick with the whole x2 first, x1 second. x2's function value is just f of x2. f1's function value is just f of x1 divided by x2 minus x1. Well, that's just the average rate of change formula, right? So this is just average rate of change. If I ever tell you to do anything with the slope of the secant line or the average rate of change of the function, I'm talking about the same thing. Let's do something a little bit different here because it's going to set up what I want to do next. So instead of calling them x1 and x2, let's call one of them just x. And let's express the second point in terms of the first. So let's just say that the second point is going to sit h units away from x. So in other words, its location is x plus h units. Well, now how do I express the slope? The same way that I did before. x2 got replaced with x plus h, x1 got replaced with just x, and then if I do x plus h minus x, I just get h. On its own, this is not particularly helpful. It will be in a minute, though. When I talk about tangent lines, I'm talking about lines that touch the curve at a single point. This is something you might have seen before in geometry, right? We talk about maybe the tangent to a circle. You might have done some proofs on that. Touches the curve at a single point, and that's what I have here. Well, the question we want to answer is how do I express the slope of a tangent line? I only have one point. However, if I look at my secant lines, I have 2 points. They are x and h units away from x plus h. Well, suppose what were to happen if I were to imagine, and I can't really animate it unfortunately, if I were to take one of these points, or this point I guess, and move it closer to x. In other words, what happens as the distance, this h distance, gets closer to 0? Well, as the distance decreases, this point's going to move along the function until it gets really, really close and almost just about touches the other point. And then for all intents and purposes, I effectively have a single point. Well, if I'm talking about what happens as h approaches 0, and we can't really get there because I only have one point and I need two, then we're talking about limits. So we want to know the limit as h approaches 0 of the slope of between those 2 points at any given moment in time. So the limit of essentially the slope of the secant line. This is what we call our instantaneous rate of change. Instantaneous rate of change. And it has a ton of applications. just about anything that can be modeled, right? We want to know the growth rate at this specific point in time. We want to know the rate of change at this specific point in time, and that's what the slope of the tangent line is for. This is where calculus comes into play. Anytime you hear slope, you're going to jump probably to something that looks like this. For example, find the slope of the curve y equals x squared at the point -2, 4. Well, I'm only given 1 point. Not a problem, because I can find the slope at a specific point by using my limit definition. So I'm just going to copy it out in general first. And let's start plugging in. So we'll copy over this limit piece. Really important to keep all of my notation together. F of x plus h. So if I were to plug x plus h into the function, I have x plus h squared minus x squared over h. Let's expand a little bit. So I have x squared plus 2xh plus h squared minus x squared all over h. And I notice that the x squareds cancel out, which is helpful. I need to eliminate the h. Oops. All right, there we go. I need to eliminate the h, because otherwise I'm dividing by 0. So I need to find a way to make that go away. Well, if I look at my numerator, I can factor out an h. I can cancel an h out of every single term up there, which will allow me to divide through. So I'm left with 2x plus h. And this is simplified as far as I can, so now I'm going to go ahead and evaluate this for h equals 0. That's what the bar means. And when I plug in 0 for h, I just get 2x. And what this number does, or this expression does, this gives me a model for the slope of y equals x squared at any point x. Any single point. So the best way to start these problems is to do them in general first. Great. So what's the slope at the point -2? So we know that the slope for any point is given by 2x. So what happens when x is -2? My slope then of the tangent line is -4. And we're done. Again, this is one of those problems that maybe out of context or in general like this, it can be a little trickier to understand or to follow. But it's just good practice right now to start with some simpler functions. Let's take a look at this one. Similar idea. Find the points on the graph of y equals 1 over x where the gradient is -1 over 4. And the first thing you might say is, what is a gradient? Gradient is IB for slope. So if you ever see gradient, I would just cross it out and replace it with the word slope. I'm looking for a point or multiple points, but at least one. So again, I should maybe jump to my formula, or my equation for the slope of a tangent line. So we'll start just by copying that down in general. Always a good place to start. Preserve all your notation. F of x plus h is just going to be 1 over x plus h. And then f of x is just 1 over x. That's all over h. And this is not going to be pleasant. Let's see here. Let's just take care of the numerator. So the denominator within the numerator is going to be x times x plus h. And I'm going to get x minus h. That's still all over h. And I did not give myself enough room, so let's move up here. So simplifying up there, I've got negative h over x times x plus h. I'm just going to leave it like that. I think it might come in handy later. If I take care of the complex fraction, that can be rewritten as negative h over x times x plus h times 1 over h. So my h's can cancel. That's helpful. And now I've got negative 1 over x times x plus h. And this is about as simplified as I can make it. So it's time to evaluate. When I plug in 0, x plus h turns into just x. So I'm left with negative 1 over x squared. So again, the slope at any given point on this function can be expressed as negative 1 over x squared. Great, well I want to know what x values produce negative 1 over 4. So when is this expression true? Well, so when is x squared equal to 4? That's when x is equal to plus or minus 2. It's one of those things again with calculus where the hardest part is the notation. Once you're through the notation and able to kind of understand what you're writing, a lot of what you're doing here is just algebra. So you want to make sure your algebra skills are sharp, you're willing to simplify and just kind of take that chance and go for simplifying something to try to get this expression, in this case, to simplify as far as you can.